High-mass stars, larger than 8 times the Sun's mass, live through multiple red giant stages, allowing them to transform into giant layered stars, with the heaviest elements at the center and layers of lighter elements lying on top. Eventually, a core of iron and nickel forms. Since heat-releasing nuclear reactions are not possible in iron, the star develops an energy crisis. No more nuclear reactions can take place, so the core will cool down, causing the atoms to move slower and the gas pressure to drop. If the core gas pressure drops, it can't balance gravity, and the star collapses. We don't know quite all the details, but it appears that as long as the original main sequence star's mass was less than 30 times the mass of the Sun, then as the star collapses and becomes denser, the collapse halts suddenly. The sudden breaking of the collapse takes place if the dense conditions allow the formation of an ultra-dense type of star called a neutron star. A neutron star has a hard surface, so when the neutron star forms, collapsing gas from the outer layers of the star will smash into the surface and bounce outwards, plowing into more infalling gas. The result is an explosion. This is the trigger for a core collapse supernova, which is also called a Type II supernova. Normally, neutrons don't appear by themselves outside the nucleus of an atom. This is because they are unstable when they are isolated and decay into a proton and an electron. However, if protons and electrons are forced to come too close together, it is possible for them to combine and transform into a neutron. During the collapse of a core of a high-mass star, the elements are squashed into such a small volume that lots of protons and electrons combine to form neutrons. This leads to a neutron-rich gas that continues to become very dense. Neutrons are particles that obey the Pauli exclusion principle that also governs the electrons in a white dwarf star. The Pauli exclusion principle means that the neutrons try to keep their own unique identities as they are forced to occupy smaller regions of space. The result is that the neutrons zoom around and create a degeneracy pressure that pushes outwards and balances gravity. A neutron star maintains hydrostatic equilibrium through this process that is called neutron degeneracy pressure. The concept of a neutron star was proposed in the 1930s, soon after the discovery of the neutron. However, many astronomers doubted the existence of neutron stars and black holes. Most astronomers thought that all stars end up as white dwarf stars when they die. In 1967, this erroneous belief changed when an astronomy PhD student named Jocelyn Bell observed pulses of radio waves. Jocelyn Bell's goal for her PhD thesis was to observe quasars using a radio telescope. Today we understand that quasars are supermassive black holes at the centers of galaxies, but in the 1960s these were mysterious, unexplained objects. During her search for quasars, she found something totally different, the pulsed radio emission with very regular pulsation period of 1.337 seconds. She suspected that this might be a new class of astronomical object, so she searched the sky in other directions and found a few more similar types of pulse radio sources. These sources of pulse radio emission were named pulsars. Soon after the discovery of pulsars, it was understood that they are rotating neutron stars. The discovery that neutron stars are a possible endpoint of stellar evolution opened up the possibility that even more exotic objects could exist, like black holes. This is the Cassiopeia A supernova remnant, which is the gas left over from a Type II supernova. The gas is millions of degrees and glows in the X-ray part of the spectrum. The small inset box shows a small point of light, which is the hot, newly formed neutron star found at the center of the supernova remnant. An artist has used their imagination to draw a picture of what the neutron star might look like, since no telescope has ever imaged a neutron star's surface with more detail than the point of light in this picture. Neutron stars are tiny stars. A typical neutron star has a radius that is about 10 kilometers, about the size of a city. Remember that white dwarf stars are close to the size of the Earth, so neutron stars are much tinier. The only object smaller than a neutron star but with the same mass is a black hole. For instance, a black hole with the same mass as a neutron star would be about 3 times smaller in radius. This is perhaps one of the least visually interesting pictures taken by the Hubble Space Telescope. It is an image of the closest neutron star, which is 400 light years away. Most neutron stars are thousands of light years away. It is not possible with today's technology to resolve features on something that small and far away. Just like white dwarf stars, neutron stars also have an upper mass limit. However, unlike white dwarf stars, the value of this upper mass limit is not known exactly. The maximum allowed mass is larger than 2 times the mass of the Sun and less than 3 times the mass of the Sun. but we don't really know the value more accurately than this. If a neutron star gains mass above this maximum mass, it will start to collapse, probably forming a black hole. The maximum allowed mass for a neutron star is very important for identifying black holes. Often we observe X-ray emitting binary star systems. The X-ray emitting properties of neutron stars and black holes are very similar, so it's easy to confuse one for the other. One way to tell them apart is to measure the mass of the X-ray emitting object, as we'll learn how to do in Module 4. If the mass is larger than 3 times the Sun's mass, then it's a black hole. If the mass is less than 3 solar masses, then it could either be a neutron star or a black hole. In all cases where the mass is smaller than 3 solar masses, astronomers have found some other evidence, such as pulsed emission from the surface, which allows for an identification as a neutron star. The highest mass main sequence stars are thought to form black holes when they run out of fuel. However, there are still many open questions about how black holes form. For instance, how massive must a star be to form a black hole? The standard limit that is usually quoted is that the mass when it was a main sequence star should be larger than 30 solar masses. However, this limit is not really known that accurately. It could be a bit smaller or a bit larger. One way to produce a black hole suggested in the 2009 Star Trek movie is to inject a planet with something called red matter. We have no idea what red matter might be, so this is definitely in the realm of science fiction. Some core collapse supernovae might produce black holes instead of neutron stars. Astronomers carefully examine supernova remnants to see if any evidence of a black hole instead of a neutron star can be found. So far, there hasn't been any discovery of a black hole found inside of a supernova remnant. However, since black holes are difficult to detect, this doesn't necessarily mean that there aren't any. Another idea is something called a failed supernova. The left image from 2007 shows the red supergiant star N6946BH1, which has a mass that is about 25 times larger than the Sun. In 2015, an image of the same star field shows no star. Astronomers did see the star get a little bit brighter, but there was no supernova explosion before it disappeared. Astronomers are now carefully watching this region to look for signs of the formation of an accretion disk. It's possible that we actually have caught a star in the act of collapsing to form a black hole. Alternatively, in some cases it might be possible for the birth of black holes to produce a burst of gamma rays. Gamma ray bursts are short-lived bright bursts of gamma rays generally seen in faraway galaxies. This movie shows the whole sky, mapped onto a sphere, as viewed by gamma ray telescopes. On April 27, 2013, the gamma ray burst 130427A occurred as shown in this movie. Over the next few hours, astronomers observed this region using telescopes sensitive to X-rays, visible and radio waves. In some cases, when astronomers observed the place where the burst occurred over the next few days, fainter light with the same spectrum as a core collapse supernova appears. In other words, it appears that some gamma ray bursts are ultra-bright supernovae. These ultra-bright supernovae are sometimes called hypernovae. It is very likely that some of these hypernovae explosions produce black holes.